line impedance and admittance. Line impedance. The line impedance of a transmission line is the complex ratio of the voltage phasor at any point to the current phasor at that point. It is basically defined as Vz divided by Iz, where Z is the point where we are finding it. So with respect to the diagram, if we have this generator, we have this transmission line of length L, and this is the terminating load impedance. And this is basically your source impedance. This is Vs source. And this is your reflected current. This is current at line at the point where the length is L. This is VR is your reflected voltage. And Z naught is the characteristic impedance of the line. So if this is the length L of the line, and this is a positive Z direction. So we always, as I explained earlier, we always calculate everything with respect to the length L. So when we will put Z, we will put equals to L minus D. So let's say we are finding it at any point D. Then this is the point D, somewhere here. In general, the voltage or current along the line is the sum of the respective incident wave and reflected wave. So V equals to V in incident plus V reflected is equals to V plus e raised to the power minus gamma Z plus V minus e raised to the power gamma Z. I equals to I incident plus I reflected is equals to Y naught. V plus e raised to the power minus gamma Z minus V minus e raised to the power gamma Z. Basically at the sending end or at the source, Z equals to 0. Then these two equations becomes Z equals to 0 put here. So it will be Is into Zs, means at this point will be equals to V plus V minus. And with respect to your characteristic impedance, we can say Is into Z naught, means at this point Is into Z naught will be equals to V plus minus V minus, because we have to consider the effect of reflected wave. So it will be in negative direction at this point. So by solving these two equations for V plus and V minus, we obtained V plus will be equals to Is divided by 2 Zs plus Z naught. V minus will be equals to Is divided by 2 Zs minus Z naught. Substitution of these two, of V plus in equation 3 point, these two equations, we will get V will be equals to Is divided by 2, means you have to put these two values in these two equations. Then we get V will be equals to Is divided by 2 Zs plus Z naught e raised to the power minus gamma Z plus Zs minus Z naught e raised to the power gamma Z. And I will be equals to just divided by Z naught. So then we can say that at any point Z from the sending end in terms of Zs and Z naught is, if you have to find the line impedance, so we have to divide V by I. So we will have it equals to Zs, just dividing these two. So it will be Z naught, Zs plus Z naught e raised to the power minus gamma Z plus Zs minus Z naught e raised to the power positive gamma Z, and denominator is just a negative sign here. Now if you are finding it at Z equals to L, the line impedance at the receiving end in terms of Zs and Z naught is given by, just put Z equals to L. Alternatively, if we are calculating everything with respect to ZL and Z naught at Z equals to L, then we have VR equals to IL into ZL. We are doing this one now, changing this equation with respect to this. Will be equals to V plus e raised to the power minus gamma L plus V minus e raised to the power plus gamma L. And with respect to the characteristic impedance, the voltage will be IL Z naught equals to V plus e raised to the power, because at characteristic impedance at length L, you have to consider the effect that the wave is reflected also. So it will be V plus e raised to the power minus gamma L minus V minus e raised to the power gamma L. Now, if we solve these two equations for V plus and V minus, we have these two. So you just have to solve these equations and you have to find the value of V plus and V minus from these equations and put them back in the standard equation of V, means these equations here. Then you get V will be equals to this, I will be equal to this. Now, if you find Z now, so it will be V divided by I. So it will be Z naught, ZL plus Z naught e raised to the power gamma D plus ZL minus Z naught e raised to the power minus gamma T. And in the denominator, there will be a minus sign here. Now, if you compare these two equations, this one at ZL equals to in terms of ZS and Z naught. This one is in terms of ZL and Z naught. So the only difference is that if you see that you have ZL here and in the above equation, you have ZS here. Otherwise, remaining equations are same. And another difference is that instead of Z equals to L, we have Z equals to, Z equals to D here. Okay. Now, if you want to find the value of ZS by letting D equals to L, then you can find the value of ZS also, because at D equals to L means now we are calculating with respect to it. So when my D is equals to this length full, then basically we are finding the sending impedance, this impedance on the sending side or at the source, you can say. So then ZS will be, just put D equals to L in this equation and you will get ZS. Also, you must know that e raised to the power plus minus gamma Z equals to cos H. Cos H is here hyperbolic. And in hyperbolic Euler equations, we don't have any complex number here. Okay. So if you put these equations and you solve for this, then you will get it in this form, but you don't have to remember them in this way. Okay. Now, if you want to find the impedance in terms of reflection coefficient or standing wave ratio, then using equation 3418 and rearranging the line impedance, then we can find it in this form, in which the following substitution is made. So you have to make this substitution. You have to rearrange it. These equations. 3.18. Yes. So if you divide this will ZL minus ZL plus Z naught, the denominator and numerator, then it will be 1 here, it will be 1 here, and it will be ZL minus Z naught divided by ZL plus Z naught. This one will also be ZL minus Z naught divided by ZL plus Z naught. And we know that ZL minus Z naught divided by ZL plus Z naught is equals to sigma L. So when you will put it, it will be 1 divided by sigma L or the reflection coefficient, and this will be 1 divided by reflection coefficient, and then you rearrange them, you will get equations in this form. Or you can say then the simple equation for the line equation at a distance d from load is expressed by this. Z will be equals to Z naught 1 plus reflection coefficient divided by 1 minus reflection coefficient. Don't have to remember this part. We already did this part already. Okay. And these are basically, if you want to go further in details of how to find the maximum normalized impedance. So it will be for you want to do it yourself. then this is the question. If you will not be able to understand, then I'll explain. Now the only topic left is Smith chart, for which I will upload some initial videos which are different from this PDF. And after that, I will come back to these pages again. Thank you.